Morning, everyone. Can you hear me on Zoom? All right. I hope Twitch can hear me too. So, did anybody do anything exciting this weekend? Fortnite tournament, studying for the midterm, all very exciting. All right. Time to get started, I think. So, today is our pause for breath day on the schedule, which is a day where we can use to catch up on anything that we didn't have time for in the previous 12 lectures. So we didn't cover everything that I wanted to cover last time pertaining to replication techniques, primary backup replication and chain replication. So I want to wrap that up. Then I want to spend a little time, and we'll do a quiz question and stuff. And then I want to spend a little time on questions that people asked on the start of course survey that I said that I would answer at some point. And then we'll open it up to questions that people have, midterm review if you want. And then if nobody has any questions, we can end early. Folks are saying there's audio problems. That's too bad. I'm not getting any notification from Zoom that my internet is unstable. So hopefully it'll improve. I'll go complain to my husband if he's like streaming Tekken right now. All right. So let's quickly recap what we said before about replication techniques. Yeah, my husband plays Tekken. He plays competitively. He would tell you that he's terrible, but I think he's pretty good. So last time we talked about primary backup replication. Let's quickly review what that is. So the idea is that there's a primary node that clients interact with. When clients want to do a write, they send it to the primary, and then there's some number of backups where when the primary gets a write, it then broadcasts that to the backups, and the backups acknowledge the primary, and this is the commit point here, which is the point at which the write can have been said to happen. And that's also the point at which the primary delivers the write to itself and then acknowledges the client. So it's only at this point that the client knows that the write has taken effect. So that's the write path. And for the read path, client just talks to the primary. So that's primary backup. It takes how many messages to hear back when you do a write? One message here, and then the maximum length of whichever one of these, plus the maximum of whichever one of these, plus one more here. So 4 messages in this round trip. Only 2 messages for reads. So primary backup has some problems. One of the problems is that the primary node has to handle everything, which doesn't do anything to improve. It doesn't do anything to take any of the burden off the primary, which was one of the goals of doing replication in the first place. So chain replication was invented. In chain replication, you've got a head node, we'll call it H, and a tail node, and some number of nodes in the middle. When the primary does a write, it writes to the head passes that on to the next node in the chain, and so on to the tail, and the tail acknowledges the client. So how many messages will that take? Well, it'll take however many replicas there are plus 1. So that's a number that's going to grow linearly with the number of replicas that there are. So it's a potentially long wait if you have a lot of replicas. And then for reads, excuse me, not that. Reads go to the tail. That's the whole point. So reads go to the tail, and the tail handles all the reads. So it's a way to split up the work between the head and the tail. The head doesn't have to do any acknowledgement of the client, so it's fewer messages for the head to have to send. So potentially, the throughput is better. Under what circumstances is the throughput going to be better? Well, the chain replication people had some discussion of this in their paper, and I actually want to show you some figures from the chain replication paper that help illustrate this. So let me find the window with the chain replication paper, 1 second. So this paper was published in 2004. It's called Chain Replication for Supporting High Throughput and Availability. And let me share it with you. Okay, so there's a lot to read here, but the particular part that I want to show you is a figure that appears in the evaluation. So here it is. So this is a figure showing request throughput. So if we look at, so there's three different figures here. If we look at the one on the left, so this number T here is the number of replicas that there are. So in this case, there are just 2 replicas for figure 4A here. So there's several different lines in this figure. Let's talk about what they are. The bottom one here, and I'll try to make this a little bigger so it's more readable actually. So the bottom line, these things that look like stars, this is what the behavior of primary backup replication is, which is what they're comparing chain replication with. This one with pluses is weak replication, and by that they mean a replication strategy where clients can talk to any randomly selected replica. So note that weak replication doesn't actually offer the same strong consistency guarantee that either chain replication or primary backup replication do. And then chain replication is this curve here with the X's. Now notice the shape of the curve. So the shape of the curve is interesting. So notice that with either weak replication or primary backup replication, the throughput decreases over time. The throughput's a lot higher for the weak replication actually, but that's because with weak replication, clients can talk to any replica, and also there's not the strong consistency guarantee. So there isn't any kind of contention on who's talking to a head or a tail, since any replica or since any client can talk to any replica. For chain replication, notice that there's an interesting shape to this curve here, where if 0% of the messages that are hitting the storage system are updates, as opposed to just queries, as opposed to, what's the value of X, then the curve exactly matches that of primary backup replication. And the same is true up here. Once you get to 50% updates, chain replication also behaves the same as primary backup replication. The point at which chain replication has the biggest advantage over primary backup replication is right about here in the curve, where they say 10 to 15% of the requests are updates. So to go back to our picture here, when 10 to 15% of the requests are writes, which are these up here, as opposed to reads, that's when chain replication's throughput has the biggest improvement over primary backup. Why do you think that's true? Why is it the case that when 10 to 15% of the updates are writes, that's when chain replication does the best compared to primary backup? But when it's either 0% or 50% or more, they perform about the same. So here's that figure again from the paper. And for the person who asked about the format of the midterm, there have been a couple of announcements in the announcements channel on our Slack. T is the number of replicas. So somebody just asked what T means. So for this one where T equals 2, there's just 2 replicas. For these other ones where T equals 3 and T equals 10, that's 3 and 10 replicas, respectively. So notice that, like, so for weak replication, for instance, notice that its throughput just gets higher and higher when there are more replicas, which would make sense because for weak replication, clients can just talk to any replica, and there's no guarantee that they're going to be getting the most up-to-date information. So if you have 10 replicas and the requests, and it's the same number of requests spread out among 10 replicas instead of 2 or 3, then obviously you can handle more requests in the same amount of time. So again, the question was this 10 to 15% number, which is about what it looks like to me, the point where there's a little bump in this curve for chain replication, the point at which chain replication does the best compared with primary backup replication. So why would that be better at that point? So my understanding of the situation is that writes take longer than reads to process. So if you were to split up the load equally between writes and reads, then primary backup replication and chain replication would perform about the same. And indeed, that's what these figures more or less bear out. So by splitting, so what chain replication does, right, is split things up equally between the head and the tail. So the tail handles reads, the head handles writes. But the head never actually has to acknowledge the client. All the head has to do is handle these write requests. So it turns out that it's not actually an even balance if we split up equally between, like if we give 50% writes and 50% reads. It turns out that that's not fair because writes take longer to process. So in that case, there isn't actually any advantage of chain replication over primary backup replication. Likewise, if all the requests are reads, then all the requests go to the tail anyway. So that's not an advantage over primary backup replication, because then there's still just one process handling everything. So this 10 to 15% seems to be a sort of magic number. So if your workload is 10 to 15% writes, then that's about the mix of writes versus reads that you want in order to get an advantage out of chain replication. And that seems to be true, at least in the experiments that they did. That seems to be more or less true, regardless of whether they had 2 replicas or 3 replicas or 10 replicas. The peak of that chain replication curve in peak in terms of advantage over primary backup replication seems to be about the same. So a lot of people are complaining about the audio quality, both on Twitch and Zoom. So my husband isn't really streaming Tekken right now, but let me just check in the other room to see if there's anything going on. Just a second. All right, sorry about that. Yeah, I don't know what it is. My daughter's watching Sesame Street videos. That's usually not such a bandwidth hog. Okay, so this is the main thing I wanted to say about chain replication versus primary backup replication. So you can go read the paper yourself if you want to, but the main thing I want to point out here is that chain replication provides an advantage over primary backup replication in this certain specific situation where you have maybe about 10 to 15% of writes. It turns out that that's actually a pretty common number for typical applications, to be maybe 10 to 15% writes and 85, 90% reads. Okay, so there's another aspect of these replication strategies that we didn't really talk about last time. And so I want to get to that today. So the thing that we didn't talk about, which some people did ask about, is how you deal with failure. So let's talk about this. So let's say that it's primary backup. So you have a primary and a couple of backups. So the client has to know who to talk to, right? They have to know to talk to the primary. And if the primary were to fail, and in that case, somebody else would have to take over as the primary, then somebody would have to be in charge of telling the client that there's a new primary. So in that case, who's going to be in charge of telling the client what to do? Well, clients have to know who to contact. So what you might have is actually some sort of proxy here. Who the clients contact, and then it's the proxy's job to pass on traffic to these replicas, and it's also the proxy's job to know who is the given who is the primary at any given moment. And then that proxy, if it were chain replication, the proxy also has to know who the tail is. They have to know who the head and the tail is. And then, of course, the replicas themselves have to know who's who, right? So if it's chain replication, and you have, say, 3 replicas, it's pretty important that the chain knows what the next member of the chain, that each member of the chain knows what the next member of the chain is, right? And it's important that they agree on that, right? Because it would be pretty bad if the head thought that this machine was the next, or it would be pretty bad if I thought that one machine was the head and somebody else thought a different machine was the head, and then that would be that would wreak havoc. So the replicas have to know who's who. The client has to know who to contact. And so there has to be ultimately the presence of some kind of coordinator node whose job it is to know who all the replicas are and what role they're playing at a given time, and keep everybody else informed of those roles. So this coordinator, which maybe I'll put over here. So the coordinator's job could be solely to tell replicas, you're the head now, or you're the tail. And perhaps to tell clients, so-and-so is the head. And to tell other replicas in the node, or tell other nodes, by the way, this replica is the head and this replica is the tail. The coordinator also has to be able to detect failures. And when a replica does fail, it's the coordinator's job to tell everybody else what that new configuration is going to be. Okay, so for chain replication, for example, if we have these three replicas, the coordinator's job is to know who's who. It's to detect failures and handle them. And it's to tell clients about who's the head and who's the tail. So maybe, if this here is machine 1 and this is machine 2 and this is machine 3, then the coordinator is going to have some state, like head is M1, B is M2, T is M3. By the way, there's an assumption here that not all of the replicas will fail. So if you have n replicas, then there's an assumption that at most n-1 will fail. And there's also an assumption that you can somehow tell when a replica has failed. So this is a somewhat more forgiving fault model than the crash model that we talked about before. Before, we said that a replica could crash by just stopping sending and receiving messages. But we didn't say that it was going to announce to everybody, I'm crashing now. So we have to be able to, we just said that a process fails by halting, it's not sending or receiving messages. But we don't necessarily know that a crashed process has crashed, right? Maybe it's still running, but all the messages are being lost. Or maybe if you're assuming no message loss, maybe the messages are just slow. So for chain replication, there's actually an assumption that processes can crash and that you can tell that they've crashed. Is this a realistic assumption? Well, yes and no. So maybe you can ask every process to periodically send you a message saying, I'm alive. And then if you miss a few of those messages in a row, then you declare it to be dead, right? So sometimes you're going to be wrong. Sometimes it might still be alive, but the I'm alive messages got dropped or delayed. So from time to time, you might declare a machine dead when it really isn't. And if you find that this happens often, you might want to increase your timeout length. And failure detection is its own whole deep topic that we could spend time on if we want to. But the short version is that perfect failure detection is impossible, so at least it's impossible in an asynchronous distributed system. So every now and then, you're going to be declaring a machine to be dead even though it's not actually dead. Anyway, we're going to assume that we can detect failures. So real quick, in chain replication, let's say that the head process fails. And let's say that the coordinator sees that it fails. So somebody just asked in chat, what's the point of the coordinator? So it's the coordinator's job to know who's who, right? To detect failures of these replicas and to tell clients who the head and tail are in chain replication, for instance. In the case of primary backup, it would be the coordinator's role to tell clients who the primary is, because the client only interacts with the primary in that case. So what does the coordinator do if the head process fails and the coordinator sees that it fails? Any guesses? Now let's just say, so somebody just asked, is the coordinator the same as the proxy? So proxy here was an example of if you wanted to, yeah, forget about this. Let's just say that the coordinator is something that's internal to this system here. And the coordinator's job is to know who all these replicas are. And the client interacts with the head, but periodically, if the head were to fail, then the coordinator is going to have to tell the client who to interact with now. This proxy was sort of an attempt to ensure that the client would always be interacting with the same replica. But that doesn't really work because we don't have any guarantee that the proxy would be any more robust to failure than the primary would. Yeah, so just establishes another backup process as the head. Good answer. So yeah, if the head were to fail in chain replication, then the coordinator just has to take the head process out of the chain, and it just makes the successor to it the new head to the chain. And then, of course, it has to tell clients who the new head is. Similarly, when a tail fails, the coordinator just removes the tail process from the chain and makes its predecessor the new tail. And then it has to tell clients who the new tail is. So in this case, because we only had 3, if the head and the tail both died, then now this process is both the head and the tail. So now we've reverted to a scenario where not only do we have any sort of throughput improvement, but we don't even have any fault tolerance either. So we better bring up a couple more replicas. What about when a middle node fails? Well, then the predecessor and the successor have to be hooked up to one another. No need to tell clients anything. So the really important question now that a bunch of you have been asking is this: what if the coordinator fails? And by the way, although I've been talking about chain replication here, in primary backup, there also has to be a coordinator to handle primary failures and backup failures and making sure the client knows who the primary is. So what if the coordinator fails? What can we do to be more tolerant of coordinator failures? Anyone know? Or have a guess? Well, the whole point of having this replicated storage system here, or part of the point anyway, of having this replicated storage system was fault tolerance, right? So we have some data, we have the value of X, right? Which is being replicated in these different places, largely for reasons of fault tolerance, perhaps also for reasons of throughput in the case of chain replication. But we have multiple copies. So you could also imagine having a bunch of copies of the coordinator. Have a bunch of coordinators, which you hope fail independently. But then those coordinators have to be consistent with each other. So how do you keep them consistent with each other? Well, are you going to implement primary backup or chain replication among those coordinators as well? And then do you have to have a coordinator for that primary backup or chain replication system and then so on forever? So this is actually the perfect lead-in to our next big topic in this course, which is consensus. And we're going to save our discussion of consensus until after the midterm. We're not going to talk about it today. But if you look at the chain replication paper, the first thing they say, which is really funny actually, is they say, well, we assume the coordinator doesn't fail, which we know is an unrealistic assumption. And they then admit that that's an unrealistic assumption. And then they explain that in the actual reference implementation that they did build, they have, instead of one coordinator process, they have a small group of coordinator processes that are among themselves running a consensus protocol to make sure that they agree with one another and essentially behave as though they're one process. So I find it really interesting and a little bit sobering too, that if we want to have consistency, because remember that the whole point of both chain replication and primary backup replication was to provide strong consistency between replicas. If we want to have strong consistency between replicas, which is what these replication protocols give you, and we also want to be tolerant of faults, which was probably the reason why we were doing replication in the first place, then ultimately we end up being reliant on a consensus protocol. And that should give you pause, because consensus is hard and expensive. So that's one reason not to have strong consistency, perhaps. If you can get away with a weaker consistency guarantee, like causal consistency, then maybe you should. But there are times when you really do need consensus, and there are times when you really do need strong consistency. So we're going to get into that after the midterm, starting on Friday. But for now, this is just a thought to carry with you, that ultimately, even if you have this primary backup or a chain replication approach, like primary backup, it's not too sophisticated, right? You just have a primary and some backup, but somebody has to be in charge. If failure is a thing, then somebody has to be in charge of knowing who the primary and who the backups are at any given time. And that problem boils down to consensus. So we end up being reliant on consensus, even in this fairly unsophisticated situation. All right. Questions about any of that? I'm scrolling back through chat here to see what questions were asked. Yeah, so one suggestion for this problem of coordinator failure in chat was assign one of the backups as a leader via some election algorithm. So this problem of leader election also boils down to the problem of consensus. Sorry about the bad quality, everyone. All right, so for fun, I thought that we would look at some questions that folks asked me on the start of course survey. So these were the questions that people submitted. About 60 people filled out the start of course survey, and this question was optional about, do you have any questions for me? There were 15 responses to this question, and I haven't actually read them all. Oh, here's a great question. Before I get to this, here's a great question in chat. Are the coordinators distributed even though they're grouped to act like a single coordinator? So that's a great question, right? So you really want, you really hope that not all of these coordinator processes that are supposed to act like a single coordinator, you really hope that they don't all fail, right? Because that would be really bad. You want at least one of them to be alive at any given time. So um, certainly if they're all, in one, let's say one data center, then if that whole data center fails, if it gets hit by a tornado, then then that's bad news for you, right? But practically speaking, it's going to be harder to do consensus the more physically distributed they are, right? Meaning it'll be slower, it'll be more susceptible to message loss and so on. So, so you really probably wouldn't do that. You would probably have them in one place and just try to do your best to ensure that failures are independent enough. That this isn't really, I mean, we talk about failures being independent in distributed systems, but failures are rarely entirely independent. So in reality, no, we just kind of do our best. And if two machines are in the same data center, we can't really be said that they fail. We can't really say that they fail independently, right? Machines that are in different data centers on different sides of the world are more independent. But I mean, they're also on the same planet, right? Um, are we going to have to locate data centers on Mars in order to ensure independence? So, and it depends what you call independent, right? And you have to come up with some definition of independent failure that's practical for your purposes. Okay, so let's see what people asked here. And I haven't actually scrolled through all of these yet myself. So so let's see. What drew you to UCSC? So I was working at Intel Labs before I came to UCSC. I was in a group called the Parallel Computing Lab. It's a really cool group. They do a lot of work that's they have a lot of, I'll say they have a lot of architecture experts there who know a ton about particular parallel computing architectures. They also have a lot of machine learning experts there. And I spent almost 4 years working there. Yeah, so Sahid works at Intel as well. So he's a fan. So it's a great organization. For me, I actually found that I wanted to do a different kind of research. And there was a job opening here at UCSC. It was actually for distributed systems, which I wasn't getting to do too much of. And I was kind of, my identity as a researcher was changing. I was becoming more of a distributed systems person. And I decided that that's what I wanted to do. And I applied and was lucky enough to get the job. This was in Santa Clara. Somebody just asked which Intel location. It was Santa Clara, SC12, for those of you who know the Intel buildings. But Intel's a good place to work. They're very family friendly, I noticed. So my daughter was born while I was working there, and they're a really supportive employer. Sahid probably knows that too. Yeah, there's still a really, really wonderful group of people here. It's just that my interests started to diverge a little bit from what my group was doing. Next question, how is it being a woman in CS? Well, you have to deal with a lot of people asking you, how is it being a woman in CS? Next question. What kind of programming languages are well suited for this kind of project? You listed some that past students have used, but no recommendations or cautions. If you don't want to recommend specifics, can you mention features of languages that might prove helpful? So it's probably a little late for me to be giving anybody advice about what language to use for the group project. But it's honestly, so Python is a really safe choice. Go has been a good choice. Java is a good choice. So my research group and I started working on a reference implementation of the course project in Haskell, and I didn't get very far. And now like 2 of my grad students are working on it with me. So you can take what you want away from that. Um, uh, Probably it would be better if I were a better Haskell programmer. Um, yeah. Um, yeah, I don't know. So I honestly wouldn't necessarily recommend that you write C for the course project, because it's just unnecessarily low level for the kinds of for the kind of problem that we're asking you to solve. And there's a similar project in CSE130, which does require writing C, but you know, it's like that's a project which has different goals. So the concerns that we have in this project are totally different. Somebody asked about JavaScript. So JavaScript can be a good choice. Some people used Node last year. I think it has some. Yeah, I think it could work. Honestly, though, like my answer to this question, and you might be surprised to hear a programming languages researcher say this, but the best language to use is the language that you and your team like, and that you feel motivated and comfortable writing. So, and this is, if that's Java, then great. If that's Python, great. If that's Go, great. If that's JavaScript, great. If it's Haskell, great. And indeed, it is more about frameworks and libraries. And I I don't know how anybody writes, let's say C++ out of like an institutional context where there's some uh, um, uh, institution-specific package management, because the package management just out in the wild world is kind of a nightmare. So yeah, you can write REST APIs in Haskell. You should check out the servant library. It's really neat. Okay, so on to the next question. Favorite Xkcd comic? I actually went back and looked at them last night to try to figure out what my favorite was. Um, and I mean, I'm still partial to, I think it's number 150, apartment full of playpen balls. But I feel like if I were, as a responsible adult, I should probably say that it's one of the ones about climate change. Is this class still a group project class? Obviously, yes. What challenges you are facing with this class that we as students can help with? I'm just really touched that somebody asked this question, because I'm just really impressed by the students in this class have a level of maturity where they care uh, about my experience teaching the class. And so, I don't know. I mean, I think you're doing the right thing by just continuing to participate actively. What is your favorite book? This is a hard one. So a novel that or a series of novels that I really enjoyed recently were the Earthseed books by Octavia Butler, um, which which would be happy to point you to. So she writes a lot of books that are sort of like post-apocalyptic science fiction, and I'm a fan, or she did. She's no longer with us. Some people are making jokes about Scheme in chat, but I should say that PLT Scheme was my first programming language, and PLT Scheme is now known as Racket, and it's still probably my favorite programming language. So, yeah. All right. Why are you so awesome? Wow, thank you. Next question. Will there be problems with having this course in an online platform? Of course there will be problems. There are problems today, but we're doing the best we can. Job prospects, obviously job prospects are not what they were before COVID-19, but they're still pretty good compared to a lot of fields. Are companies looking for people to work on distributed systems? Absolutely, yeah. So, and in fact, a lot of systems are distributed systems that you might not expect are. So I'm hoping that what you learn in this class will end up be relevant to a lot of jobs that you might have not ever thought were even necessarily about distributed systems. Next question. At some point, either directly or with the class, can you share with us your experience of getting into academia? So I moved back and forth between academia and industry. So I did undergrad. I then I worked in industry for a few years. I worked for for a terrible startup that failed, and then I worked for a large publishing company. Then I went to grad school, and I did some different kinds of internships when I was in grad school. Some more academic than others. Then I worked in Intel Labs, which was an industry research job, and then I came here to UCSC. So I've been bouncing back and forth, and I think in computer science it's much easier to do that bouncing back and forth than it is in a lot of fields. I think that academia is an option that's underexplored by a lot of computer science undergrads. So you might not think that it's an option for you for whatever reason, but I urge you to reconsider. How distributed systems is relevant in the industry. I hope that this will be answered especially by our guest speakers. What sorts of machine learning and deep learning applications exist in distributed systems? So there's quite a lot. So just to throw out an example that has to do with what we talked about today. So this question about like, you have a coordinator, what if the coordinator fails? Or you need to elect a leader. Well, you might want to try to pick one that's unlikely to fail, right? And that could potentially be a machine learning problem, just to throw something out there. But there's a whole conference called SysML that's about applications of systems to machine learning and applications of machine learning to systems, which I'd recommend you check out if you're interested in this. And this is all Google ever does, right? Google turns machine learning problems into systems problems at a massive scale. So, I mean, like I can't even scratch the surface of how to answer this question, but there's an enormous number of applications that marry machine learning with distributed systems. And hopefully this last question about jobs has already been answered as well. Okay, so that's it for the start of course survey questions. Thanks for everybody who submitted questions. In the time left, who has questions that that I can help answer for exam review or anything else? And I'm open to answering questions either on Twitch or on Slack. And if nobody asks any, then we'll go home early. Oh, right, we already are at home. We'll end the meeting early. How much about replication do we need to know for the midterm? Yeah, so the stuff that I talked about today about coordinator failure and so on, that won't be on the midterm. Oh, somebody just asked, what about the quiz question for today? Sure enough, I had a quiz question set up for today and I didn't give it to you, so let's do that. Here is today's quiz question. And the form should already be open. Yeah. I will share the link. Thanks for reminding me. Okay, so while people are answering that, let me try to answer this question about replication for the midterm. So uh, on the midterm, you won't have to know anything about what we talked about today, about like what if the head node fails, what if the tail node fails, what if the middle node fails, what if the coordinator fails, that sort of stuff. Instead, there will be questions that are actually about what is primary backup, what is chain replication, just kind of at a high level. So if you're caught up in terms of last lecture, then you should be in good shape. How many questions will there be? So this was answered in the announcement about the exam. I think I said there will be about 15 questions. Yes. You will not have to draw and upload anything for the midterm. Good question. So yeah, so on a typical exam that I would give in person, um, it would be there would be some drawing involved. I would ask people to draw pictures. Um, so I spend a whole lot of time in this class drawing pictures like this, obviously. So uh, I like to ask students to do that too. But the logistics of it is just too hard to handle for a midterm length exam. On the final, we may ask you to draw and upload something, and we will still have to work out the logistics of that. But on the midterm, we will not ask you to draw any pictures. It's all going to be uh, questions that you answer with one or two sentences. Um, uh, and or let's see, I think some of them are answer in 1 to 2 sentences. Some of them are like answer in 2 to 4 sentences. So there's a question on Twitch. What's your take on free and open source software and the big push by universities by UCSC to use platforms like Zoom and ProctorU? So it's been interesting how ubiquitous Zoom has been across higher education. Like this is not just UCSC. Uh, Almost every an educator that I know uh, has been using Zoom, and it's not just higher education either. Uh, so yeah, like it or not, um, Zoom seems to have cornered this part of the market. So I don't love Zoom, uh, and indeed, students in this class have the option of not using Zoom, right? They have the option of just watching on Twitch. Um, Now, there have been a lot of privacy complaints about Zoom, but I'm not sure that most of the alternatives are much better. Now that isn't to say that we should just resign ourselves to software that's horribly insecure and privacy invading, um, but um, but I don't necessarily have a better solution in mind. Um, uh, ProctorU, I think, is pretty creepy, and I'm not alone in thinking that. And a lot of my colleagues refuse to use it, and I refuse to use it as well. I will also say that in terms of like commitment to using free and open source software, um, there's and it's so it depends, right? If you don't want to use anything but free and open source software, well, right now you're using Slack, right? If you're in my class, which isn't free and open source, right? Or you and neither is Twitch. So the only difference is that they happen to be running on somebody else's computer instead of yours. So um, if the issue is installing proprietary software on your own machine, then you can avoid doing that. But I hardly think that that's much of a meaningful distinction. So I, I have resigned myself to using a fair amount of proprietary software for certain aspects of doing my job. And no, maybe maybe that means that I'm morally compromised. I don't know. Somebody asked me to go over the answer to the quiz question. Let's see. Has everybody who was going to answer the quiz done so? I'm not sure. Yeah, I'm going to give it a little more time to see if anybody else wants to answer the quiz. But honestly, if you want to know the answer to the quiz question, just go back and watch this lecture. Other questions? Questions about the exam? One question is, will the midterm questions be in similar style to the quiz questions? Okay, so I guess so. So for the midterm, unlike the quiz questions, we actually grade you on the content of your answer. So I'm hoping that people will put a little bit more effort into how they answer the questions. So we typically ask you to write, anywhere like 1 to 2 or 2 to 4 sentences, and we'll specify how long of an answer we expect for the midterm questions. But the flavor of the questions will be similar. Some of the questions will be a little will perhaps take a little bit longer to understand, right? Because we'll ask you to, for example, look at a diagram and then answer questions about the diagram. So that'll take a little bit longer to kind of take in the question and understand what it's asking. There's a question for the algorithm. Should we just know how to apply it and understand how it works? I'm not sure I understand exactly what you're asking here, as opposed to what. So if you're just wondering what's going to be covered, it's going to be everything from the lectures so far. So you can go back and look at the schedule, which I could bring up right now. So anything from the first 12 lectures is fair game for the exam. Yeah, I wouldn't say the main difference from the midterms that I do in person on paper is that, so on those midterms there were typically more questions, and more of the questions would be, let's say, multiple choice and fill in the blank. So I opted this time to have fewer questions and have more of them be like short essay questions. I don't like the word essay question because that implies that you have to write something long when I'm really just talking about a couple of sentences, but I don't know a better word. A short essay question, I guess. And then also on a typical exam, we'd ask people to draw diagrams, and we're not doing that this time. So yeah, hopefully it won't be that different. Okay. So it doesn't look like there's too many more questions. Oh wait, somebody's asking a question. I'll wait for that. Oh, I guess not. All right. In that case, I think we're going to end a little bit early. Good luck on the midterm on Wednesday. I won't be streaming on Wednesday. And then we'll see you on Friday for class again. Thanks.